Hi, my name is John Moulton, and I'm a rising senior at California State University, Stanislaus. Last semester, in the spring of 2020, I took a cure course offered by the Department of Chemistry called Advanced Biochemistry Lab, and I'm going to be going into depth on how we went from benchtop to laptop. We began the spring of 2020 semester using an oxygenase enzyme in the lab. The goal of our project was to obtain an oxygenase variant library of the 19 possible variants for the amino acid position assigned to us by Dr. Schara. We worked in teams of 2 or 3, and if we were going to reach our goal, we would have used the mutants for either biopharmaceutical applications or green chemistry applications. So we began our project by performing a saturation mutagenesis via a 3-step overlap polymerase chain reaction. And a couple of different techniques that we used were DNA extractions, PCRs, running gels, as well as a few others. As we switched to online learning, Dr. Schara decided to take our cure course in a whole new direction, computational modeling. We're still working with the same oxygenase enzyme, however, we now have our own individual projects. Each student was assigned a different amino acid position to mutate and 3 different drugs to dock to each mutant. The position I was assigned was amino acid position 103 and the drugs omeprazole, bupropion, and chlorophenyramine. We were then instructed to use PyMol to get a 3D model of the enzyme, as well as the 19 other variants. Once these variants were obtained, we used a program called AutoDockVina to dock the drugs to the enzymes. By docking the drugs to the enzymes, we'd be able to theoretically determine which drug-enzyme combo would be the best.
The pictures below show my results for the first part of the experiment, where I was trying to determine which drug had the greatest affinity to the wild-type enzyme. The results circled in red showed the delta G values for each protein-ligand complex, and as you can see, the complex with the lowest delta G value and the greatest affinity is the one on the left, with a delta G value of negative 6 kcal per mole. The drug in this complex was omeprazole. I then moved to the second part of the experiment, which was to determine which mutant omeprazole complex had the greatest affinity. After docking omeprazole to all the variants, there were only 2 with a greater affinity than the wild-type enzyme. Both the isoleucine and valine variants had a slightly greater affinity to the drug than the wild-type. Here is a visualization of the drug docked to both the isoleucine mutant on the left and the valine mutant on the right. These images were generated by PyMol. If we were able to go into the lab after this experiment, I would have isolated both the isoleucine and the valine variants of the enzyme and tested their affinities to the drug.
From my perspective, this course modification had both a positive and a negative impact on me. Beginning with the negative, it didn't allow me to get the research-based, hands-on experience that I was expecting to get before I applied to grad school. However, I believe it had a much greater positive impact on me. It allowed me to realize how important computational molecular design is and how much time it can save you if you have access to it and know how to use it. This modification sparked my interest so much so that I'm currently looking for computational labs to do research in.